In this topic, it will be explained the priorities for operating the rotary kiln that must be followed for optimal operation. This topic contains 1. Kiln operation priorities. 2. Kiln system stability. 3. Main parameters, trends, and absolute values. 4. NOx analysis. Rotary kiln operation priorities include 1. Safety, one of the most important operational priorities rotary kiln. Protection of the personnel working in and around the kiln system is a basic safety rule that must be strictly followed at all times. 2. Protection of the equipment. Around the kiln, the safety of the equipment is mainly related to overheating problems, and could be a. Back end of kiln. A. Do not exceed 450 degrees at precipitator inlet. B. Feed. A. Do not exceed 10 minutes, without feed, as the feed end temperature would go high. This picture shows inlet rotary kiln. C. Chain inlet temperature. A. Do not exceed metallurgical maximum temperature of chain system, usually approximately 1038 degree. D. Burning zone. 1. Do not overheat, keep the raw load near end of flame. 2. Set a maximum amps level on kiln motor. E. Cooler. 1. Avoid overloaded cooler grates, cut kiln speed down to protect the cooler grates. 2. Avoid high exhaust gas temperature, could damage dust filter system. 3. Avoid high clinker temperature, could damage the clinker evacuation circuit. This picture shows burning zone, cooler, and kiln. Three. Quality. To produce a well-burned clinker with good free lime, at the desired liter weight. 4. Stability. Firstly, continuous operation should always have priority over maximum production. Secondly, stable kiln operation is the key to long refractory life, high fuel efficiency, and uniform quality clinker. 5. Optimization. A. Strive for optimum production level, at the lowest possible cost. Kiln system stability, it depends on 8 main factors. 1. Stable feed. It is divided into 2 parts, chemical and physical. A. Chemical. Firstly, feed quality range should be plus or minus 0.4% in CaO, plus or minus 0.4% in SiO2, plus or minus 0.2% in Al2O3. Secondly, C3S variations in clinker not to exceed plus or minus 3%. Thirdly, approximately 25% relative potential liquid phase in the clinker is good for kiln burning and fuel saving. B. Physical. Firstly, good and accurate feed rate indication. Secondly, way feeder should be linear at low, medium, and high feed rate. Thirdly, good calibration by physical weight of the material should be done at every major kiln shutdown. Fourthly, good feed and speed ratio. 2. Stable dust reintroduction to kill. Firstly, dust collector cleaning cycle sequencing. Secondly, dust circuit configuration should provide stable reintroduction. Thirdly, monitoring of the dust return flow is an added advantage. Fourthly, if dust wasting is required, wasting should be done in such a way not to upset the dust return to the kiln. 3. Stable water spray injection in kiln or in conditioning tower. Firstly, good spray injects into gas stream, not in material load. Secondly, good regulation of water injection, with respect to ESP inlet temperature control, will cause changes in kiln oxygen level if water flow is not changing smoothly. This picture shows conditioning tower. 4. Good chain system design, wet and long dry. Firstly, act as a good dust curtain, dust trap. Secondly, wet kiln design needs to favor a good plastic zone in order to prevent ring formation. Thirdly, chain tonnage should be between 12 to 14% of clinker production for large kiln, and 10 to 12% for small kiln. Fourthly, good chains should stand high temperature, so that in return enable high production rates. 5. Good control of hood pressure. Firstly, hood pressure control is critical, because it prevents the cooler variations to upset the burning zone conditions. Secondly, hood pressure set point should be set as close as possible to zero, while remaining negative. 6. Stable secondary air temperature. Firstly, the temperature variations during normal operation should not exceed plus or minus 29 degrees. Secondly, good regulation of the cooler under great pressure is then required, with a thick clinker bed depth. Thirdly, the secondary air temperature should be as hot as possible, without damaging the nose ring or the refractory at the kiln discharge section. 7. Good production level. Firstly, lower limit, under 60% capacity kiln tends to become unstable. Secondly, upper limit, production restriction due to 1. Kiln diameter, maximum flame size, flame erosion on kiln walls. 2. ID fan capacity, no leeway on oxygen level. 3. Precipitator capacity, cooler grates overloaded and high clinker temperature at cooler outlet. This picture shows ID fan, preheater. This picture shows precipitator, cooler outlet gas, cooler, tertiary air, rotary kiln. 8. Constant fuel quality and quantity. Firstly, constant fuel quality and quantity, to allow constant heat input inside the kiln. Main parameters, trends, and absolute values. 1. Back-end temperature. 2. Set point varies with the kiln production level. 3. Set point varies with the condition of the chain system. 4. Absolute value allows one to draw conclusions about efficiency of the kiln system and the kiln operation. 5. Trends is important for the kiln operation. 6. With the use of water spray in the back end, the water volume will show the reactions of the back end temperature. Material temperature. Firstly, slow reaction compared to gas temperature. Secondly, in wet process kiln, material temperature is a good indication of the behavior of the material in the chain system. Chain gas temperature. 1. This temperature is generally a limiting parameter for the kiln operation. 2. The chain gas temperature set point is generally fixed by the metallurgy of the chain system and its design. 3. Absolute value is very important and must be held below the allowed T for the chain system. 4. The trend is representative but has slow reactions with respect to the back-end temperature. 5. Very important to the kiln operation in order to make a good material preparation before it reached the burning zone. Burning zone temperature. This picture shows an area burning zone at kiln. 1. Importance of this instrument is often overestimated. 2. Precise only when kiln conditions are clear. 3. The secondary air dust influence in the indication of the instrument and readings are in error when kiln gets hot and dusty. 4. It must be correlated with the kiln amps indication and the secondary air temperature to ensure the validity of the reading. Shell temperature scanner. 1. Importance of this instrument is underestimated. 2. It is often used only to detect hot spots on the kiln shell, an estimation of brick thickness, and coating in the kiln. 3. On bigger charts, it gives a good indication of the burning zone temperature profile. 4. It is one of the fastest indications of a slowly moving ignition point in burning zone. 5. It is a very good indication of flame variations due to the burner pipe position, flame shape, and direction. Good indication when adjusting flame in kiln. 6. Ignition point movement and operating conditions which are affecting the temperature profile of the burning zone. Absolute value is important to detect hot spots and rings. Trend indicates changes in the burner system, kiln speed. This picture shows shell temperature scanner. Kiln drive amps. 1. It is the most important sensor used to evaluate the burning zone state. 2. The running set point will change according to the raw material composition. 3. Amperage value changes with ring formation. 4. Amperage value changes with the size of the clinker. 5. The absolute value is important only when amperage is high. Fuse protection limitations. 6. The trend is a very good indication of burning zone length and temperature, therefore the amps should be recorded in such a way to give a good indication in its variations. 7. A drastic increase of the amps trend, followed by a fast decrease is an indication of loss of coating or a broken ring inside the kiln. 8. A target amps range should be established, depending on raw mix and other factors, through which this variable can fluctuate safely. 9. A drastic increase in amps could indicate a possible mechanical condition problem. NOx analysis. Firstly, essentially it is an indication of the flame temperature. Secondly, higher is the flame temperature, the higher will be the NOx concentration. Thirdly, NOx content in the flue gases in the smokestack originate partly from high temperature synthesis in flame from oxygen and nitrogen. Fourthly, NOx level has been measured in the range between 500 and 2000 ppm in the Lafarge group. Fifth, NOx increase with excess air and is strongly correlated to low excess air levels. Sixthly, at higher levels, 3% and greater, NOx is weakly dependent on excess air. Seventh, correlation between burning zone temperature and NOx level is good. Eighth, NOx is generally, but not systematically correlated with the kill drive amps. Ninth, NOx gives a truer picture of burning conditions. Kill drive amps will change due to ring formation and degradation, whereas NOx signal will not. 10th, NOx correlates better with clinker liter weight than free lime. 11th, NOx is affected by fuel changes. Natural gas flames yield the highest. 12th, NOx level. All the factors having an impact on the flame temperature will affect the NOx signal like the following: the secondary air temperature, the primary air temperature, the burning zone temperature, chemical composition and fineness of the fuel, the air and fuel ratio, and the flame environment, reduced or oxidized atmosphere. A quick decrease in the NOx signal is an indication of the burning zone temperature dropping. A slow and even decrease on the NOx signal is an indication of a slow cooling of the burning zone and is related to a bad material preparation from the kill back end. On the automatic kill control system developed by Lafarge, the program is giving 30% of it as evaluation of the burning zone state to the NOx signal, 55% to the kill amps, and 15% to the clinker temperature at the kill outlet. Secondary air temperature. It should be kept as stable as possible by the automatic cooler control system, plus or minus 39 degrees. Absolute value is not important, because most indications are incorrect due to instrument inaccuracy. Trend is very important as it shows variations of material from the kill and the gas temperature variations to the kill. The secondary air temperature should be as high as possible in respect of the various refractory temperatures in front of the kill. This picture shows secondary air temperature. Hood draft. Absolute value is important and is automatically controlled at a constant value, usually looped to cooler exhaust fan damper or fan. It should be low as possible, to reduce in leakage. It is the separation between cooler and kill. And it should be always constant to avoid influences of changes in the cooler gas flow to the kill operation. A poor regulation of the signal will induce variations in the kill gas flow, and could bring the kill into cycling. Feed end draft and ID fan draft. Trend and absolute value help to detect build-up in the kill. This is a very important sensor if many ring problems occur in a plant. Cooler exhaust gas temperature. Trend will give you information about the temperature profile in cooler gas flow variations and clinker temperature. Absolute value is an important limitation for protection of the dust collection system. The cooler exhaust temperature is a more reliable clinker discharge indication than the clinker temperature. In this picture shows the exit of gases from the cooler, in addition to the secondary gases entering the kill. Clinker discharge temperature. Trend has no importance for cooler operation. Absolute value is an important limitation for safety of the clinker transport system. Clinker temperature measurements are generally not very accurate. Under great pressure, the absolute value should be maintained constant with automatic control. The value varies with the cooler bed depth and with clinker size. It must be held constant in order to achieve a constant secondary air temperature. Also, only a constant airflow can allow the relationship between undergrade pressure, bed depth, and secondary air temperature to be valid. Variations of the undergrade pressures. Trend are reflected by variations in the cooler grate speed. Undergrade pressures together with cooler drive amps should give an indication of the clinker size. Undergrade pressure set point should be at least 5 inches, H2O, in order to get good heat recuperation from the clinker bed in the cooler. Oxygen analyzer. Trend and set point value are very important. It should be maintained as constant as possible. It can supply indications about general kill conditions, burning zone, and back-end temperature. One of the best indications when the kill is pushing, to indicate if the push is still on or over, related with the amount of CaO in the kill gases. It should be kept as low as possible when the kill is stable, without going into CO range. However, when using coal or coke, set point should be increased to overcome the fuel quality variations. Thank you for showing interest. With family greetings, everything about the cement industry. I hope for your support by subscribing to the YouTube channel.